Find the area of triangle BEC in feet squared. In this problem, 5 points A through E make up the vertices of two triangles, which share point E. The angle at point E for both triangles is 90 degrees, and the bearings of side lengths AE and AD are given. The length of line segment AD is also given. And we know these two triangles are similar because they share the same angle measurement at point E, and the line segment BC is parallel to line segment AD, since the offset of 40 degrees is arbitrarily located along the lengths of these line segments. The area of triangle BEC equals 1/2 times the length of side BE times the length of side CE times the sine of angle BEC. Since angle BEC equals 90 degrees and the sine of 90 degrees equals 1, then the last term in this equation can be removed, and the area equals 1/2 times the length of line segment BE times the length of line segment CE. The length of line segment CE equals the length of line segment DE minus the length of line segment CD. The length of line segment DE equals the length of line segment AD times the sine of angle EAD. In this equation, the length of line segment AD is given as 612.4 feet, and angle EAD equals the azimuth of course AD minus the azimuth of course AE. The azimuth from point A to point D equals 180 degrees minus 69 degrees 55 minutes, which equates to 110.083 degrees. The azimuth of course AE equals 88 degrees 35 minutes. This makes the angle EAD equal to 21.5 degrees. Plugging in the values of angles EAD and side length AD, the length of line segment DE equals 224.44 feet. Next, we'll solve for the length of line segment CD. To do so, we'll focus in on this area of the figure. And if we define the point C prime as the orthogonal projection of point C onto line AD, then we can equate line segment CD to the length of line segment C prime C, divided by the sine of angle C prime DC. The problem statement shows the offset between lines AD and BC equals 40 feet. Therefore, we know the length of line C prime C equals 40 feet. Angle C prime DC is the same as angle ADE of the large triangle, which equals 180 degrees minus angle AED minus angle EAD. In this equation, we know angle AED is 90 degrees because we're dealing with a right triangle, and we calculated angle EAD earlier in this problem, which was 21.5 degrees. This makes angle C prime DC equal to 68.5 degrees. Next, we'll divide the length of side C prime C by the angle C prime DC, and the length of side CD equals 43.0 feet. Next, we plug in the lengths of line segments DE and CD, and we calculate the length of line segment CE equals 181.44 feet. Next, we have to solve for line segment BE. The length of line segment BE equals the length of line segment AE minus the length of line segment AB. The length of line segment AE equals the length of line segment AD times the cosine of angle EAD. The length of line segment AD was given in the problem statement as 612.4 feet, and angle AED was calculated earlier in this problem to be 21.5 degrees. 612.4 feet times the cosine of 21.5 equals 569.8 feet. To find the length of line segment AB, we'll focus in on points A and B and define the point B prime as the orthogonal projection of point B onto line AD. Now we can equate the length of line segment AB to the length of line segment B prime B divided by the sine of angle AED. From the figure, we know the length of line segment B prime B equals 40 feet, and we already calculated the angle EAD equals 21.5 degrees. This makes the length of line segment AB equal to 109.14 feet. Plugging 109.14 feet in for length AB and 569.8 feet in for length of AE, the length of line segment BE equals 460.66 feet. Finally, we can substitute the length of line segments BE and CE into our equation for the area of triangle BEC. And we find that the area of this triangle equals 41,791 feet squared. When reviewing the possible solutions, the answer is D.